Hey everybody, this is Kevin Wallace, double CCIE and Cisco Press author, and in this video we want to talk about fiber optic cabling. To begin with, let's think about physically how fiber optic cabling works. Here's an example of a very short fiber optic jumper cable that we might plug into a piece of equipment. Notice that we have two strands of fiber in each of these cables. One is for receive and one is for transmit. Now, by the way, the particular type of connector we have on this jumper is called an ST, or a straight tip connector. This is an MTRJ connector, and later on in this video we'll take a look at some of the different types of connectors we might have. But first, let's think about how this really works. How do we transmit binary data, ones and zeros, over a fiber optic cable? Well, it's going to use light. We might use LEDs. Commonly we use lasers. But the question is, if I shoot a laser down one of these glass strands, how does it stay in that glass strand and not just get dispersed? Well, here's the way it works. Have you ever taken a glass of water and put a straw in it, as an example? And have you noticed how that straw seems to bend in the water? The reason that we get that effect is that light actually travels at a different speed in water as compared to air. It's a little bit slower in water, and air is a little bit slower than a vacuum. But that's what we're going to do. We're going to change the index of refraction of the glass to make it bend back on itself. Here's what I mean. Let's imagine that we've got this fiber optic cable. And this is the inner core. This is where the light is actually traveling in the fiber optic cable. But surrounding that core, we have the cladding. So we've got this outer type of glass. Inside of that, we have the core where the light actually travels. And the index of refraction is very different between the outer cladding and the inner core. So much so that when, let's say we've got a laser coming in here, when the light hits the boundary between the core and the cladding, the index of refraction is so great that, much like that straw appearing to bend in a glass of water, it bends the light. Well, here, the indices of refraction are so different that the light actually bends back on itself. It's going to bend back like this, and you see, it keeps bouncing back and forth all the way down the fiber optic cable. However, if this diameter is too large, here's what can happen. Let's say that we've got another path of light going like this. This is called a different mode of propagation. The laser came in at a slightly different angle, and as a result, it's not bouncing as much as the original beam of laser light did. Can you imagine if we extended this for 2 or 3 kilometers? The distance being traveled by each beam of light is quite a bit different. This one's bouncing back and forth, back and forth, back and forth a whole lot, and this one's barely bouncing at all. We might have yet another mode of propagation where the light almost goes right down the middle. It's going to get there faster. Can you imagine that if we had different photons representing different binary bits, that it's possible that these bits could arrive out of order? Because one bit is going back and forth, back and forth, back and forth. Even though it went first, it might not arrive before another beam of light that's going right down the middle of the fiber optic core. What I'm describing here is something called multi-mode delay distortion. Multi-mode delay distortion occurs when we have different modes of propagation extended over a long distance. And that can result in corrupted data. Maybe the data originally was we had a 0, we had a 1, we had another 0, and we're going in this direction. Because of all the different modes of propagation, it actually might arrive out of order. It might arrive as something like 1, 0, 0. We've corrupted our data. So to prevent this from happening, there's a couple things we can do. Number one, we can limit the distance. In fact, we're going to take a look later in this video at some of the distance limitations surrounding different types of fiber optic cabling. So if we don't go too far, then this is not going to be an issue. Another way to address this issue is to simply have a smaller core. With a smaller core, there's not room for all these different modes of propagation. There's only room for light to take one path down that fiber optic cable. And as a result, we don't have to worry about this multi-mode delay distortion. You're oftentimes going to see this type of fiber optic cable referred to as multi-mode fiber, and the bottom type is referred to as single mode fiber. Those are a couple of different types we have. Now, let's go out to some slides and take a look at some specific types of cables, connectors, and distance limitations. Now that we understand a bit about the optics in fiber optic cables, let's talk about some of the specific connectors we might run into. One that I showed you just a few moments ago was the ST connector. Sometimes that's called straight tip or bayonet. You insert this in the connector and you might be able to see that there's a spring inside the connector. You push and twist and release, and that spring creates tension to hold the connector in place. And these are fairly common. Another type you might run into is an LC connector. And some of the terminology here might vary depending on where you're reading about it. LC, some literature will tell you, stands for lucent connector or local connector or little connector. But notice that there is a push-down plastic tab that allows you to secure and then to release one of these LC connectors. An SC connector allows you to push this connector into the receptacle, and to remove it, you just push again, and it pushes in and it unlatches. And what SC stands for, again, might vary based on the literature you're reading, but some of the literature calls it a subscriber connector, or a standard connector, or a square connector. The other type of connector that I showed you just a few moments ago was an MTRJ, and the thing that's really unique about an MTRJ is it contains both fiber optic strands, one for transmit, one for receive. It contains both in a single connector, which allows us to have a higher density of connectors. An MTRJ, it might stand for, depending on your source, Media Termination Recommended Jack, or Mechanical Transfer Register Jack. Now, let's imagine, and we'll just use an ST connector for this example, but let's imagine that we have a couple of ST connectors in a fiber distribution panel where we have the ends of these ST connectors bumping up against one another, and we're trying to send a light source through one connector into the other connector. If they meet with very flat surface, hopefully we're going to have very little loss. There are fiber optic polishing kits to try to minimize this loss, but there's going to be some reflection. When the light comes in, let's say from the left-hand side, and it hits that interface between the ST connectors, hopefully almost all of the light is going to pass through and go into that other connector and on to its destination. But no matter how much we polish, there's going to be a little bit of reflection. And that reflection could come back to us. It could come back to the optical source, the laser, and actually damage that laser in some cases. So many people, instead of using this approach where we have a flat surface touching a flat surface, which is known as a UPC, an ultra physical contact, some people prefer to use an APC, which is an angled physical contact. Here, when we put these connectors together, they don't completely touch. It's not a flat surface meeting a flat surface. There's actually an 8-degree angle between these. And this is called, again, an angled physical contact. And the idea is the tiny bit of reflection that we get is not going to go straight back and damage the optical source. It's going to be dissipated in the cladding of the fiber. Now let's wrap up this video by taking a look at some of the distance limitations of different types of fiber optic cables. And we'll do this by considering some of the Ethernet standards that are popular out there. If we have twisted pair cabling and we're running fast Ethernet, we're running a 100 base TX, then on something like category 5 or higher, we're going to be able to send 100 megabits per second for 100 meters. If we're doing 1000 base T, that's a gig. We'll be able to send a gigabit per second over, again, 100 meters. Now let's go into our fiber optic cabling. If we have 1000 base LX, the 1000 tells us that we're transmitting at 1 gigabit per second, but the distance limitation is a bit different depending on whether we're using MMF, multi-mode fiber, remember the multi-mode delay distortion, or SMF, single-mode fiber. With multi-mode fiber, our distance limitation is 550 meters, but if we just have a single mode of propagation, if we're using single-mode fiber, we can go for 5 kilometers. Another Ethernet standard that uses fiber is 1000 base SX. This is a multi-mode fiber standard. It again has a throughput of 1 gigabit per second, and here the distance limitation varies based on the diameter of that core. It's really common to have 62.5 micrometers as the diameter of a core in a multi-mode fiber. That's what I was showing you a few moments ago. And if that's what we're using, the distance limitation is 220 meters. But if we have a smaller core, still multimode fiber, we can still have multiple modes of propagation, but not as many. Our distance limitation is going to be 50 micrometers. And hopefully that gives you a sense for how distance limitations can vary based on the type of fiber optic cable that we're using.